Today we're talking about how to graph planes in 3D, and we'll get to see what the equation for a plane looks like, so that's pretty fun. It's actually really challenging to draw planes in 3D, you can probably imagine, but here's a picture of sort of a flat plane leaning up against the corner in a room. It's rectangular, but technically a plane is infinite, and so we would have to imagine that going infinitely into the walls, through the walls, down into the basement, but that flat surface is a piece of the plane we're trying to picture. And this is what an equation for a plane looks like in 3D. You can see that all three variables get involved, and it almost looks like sort of a linear equation in 2D because it doesn't have any funny squares or anything going on, just single variables added together. The way that we're going to try to envision this is we're going to imagine where it cuts through the x-axis, the y-axis, and the z-axis. We're going to do that by finding the x-intercept. If we were on the x-axis, there's one thing I know. I know that the y value and the z value are 0 because we're on the axis. So what I'm going to do is I'm going to substitute that into the equation, a 0 for y, 0 for z, and I'm going to solve. So we've got nothing plus nothing. I've got 2x equals 4. Divide that 2, I've got x equals 2. So my y-intercept is the point 2, 0, 0. We probably shouldn't just write x equals 2. We should write 2, 0, 0 is the x-intercept. All right, so let's find that y-intercept the same way, except when you're on the y-axis, your x value and your z value are both 0. In the equation, here's what that'll look like. Two times 0, 4 times 0, that's all nothing, and I find out that y equals 4, which tells me that the point 0, 4, 0, 0, 4, 0 is the intercept on the y-axis. Last one. We're on the z-axis, so we haven't gone forward, we haven't gone to the right or left. Zeros are gone, divide by 4, and I get z equals 1. That's the point 0, 0, 1. So now I can see where that flat plane is going to cut through my 3 axes. In that first octant, we'll be able to see just a little bit of the plane. And this is where it gets tricky because I have to try to graph that plane. Well, here's what I'm looking at. I'm looking at a flat surface that touches these 3 points. And if you connect 3 points, you get a triangle, and it just so happens that a triangle is flat like a plane. And so this triangle, if you can imagine that made out of wood or something, that triangle leaning in the corner of my room represents the plane. Of course, that plane would go infinitely into the other octants. Not all of them, but down here, up there, over there. So we have to just sort of use our imagination and imagine that being an infinite plane. Some people try to draw what it would look like in those other planes, just kind of extending. I don't know if that makes it any more believable, but that would show those other parts of the plane extending in every direction. And finally, we're going to find the XY trace. That word trace is just keyword for if the z-axis didn't exist, what would you see? You wouldn't see any of this flatness. All you would see is the part on the floor. And the part that intersects the floor is actually just a straight line. And so when we calculate the XY trace, we're going to be finding an equation for a line that's just on the XY plane, which is what we're used to in our usual algebra class. Since we're on the floor, we know that the z value is 0. We don't have any up or down, so we're going to go back to that plane. 2x plus y plus 4 times 0 equals 4. 4 times 0 is nothing, and so we've just got 2x plus y equals 4. And that's the equation of the xy trace. You can imagine if you subtracted that 2x over, That would be in a form that maybe you recognize a little more, mx plus b. So that's the equation of that line where the plane intersects the floor. And that is graphing planes in 3D.